Good morning, everyone, or good afternoon, or wherever you are. Hi, my name is Dorothy Heinrich. I'm a consultant for the Red Cross Climate Center. And we are running a session on science and technology and the use and newest developments on the use of science for early warning and early action. And this session is supposed to be a carousel talk where different students are presenting their work and the advances that they're making in science and tech in this space. And so the whole point is to allow students to, showcase their work, talk about kind of the ideas, the groundbreaking stuff that they're doing, and kind of discuss with you and kind of create a virtual space in which everyone is comfortable kind of talking and exchanging on these fascinating topics. So we have 6 presenters today for 5 sessions, and 5 of which are students under the SHEAR program, which is funding science for humanitarian action, which you might be aware of. And so they're funded under this project, and the idea is to allow everybody a platform to talk about all these topics. And so we. Hi everyone. Hey, can you hear me? All right, brilliant. Welcome to this session. My name is Dorothy Heinrich. I'm a consultant for the Red Cross Climate Center. And I was asked to run the session on science and technology for early warning and early action. And the point of the session is to kind of present a carousel of speakers who are working in this space and who are pushing these advancements in early warning using science and technology in various different and creative ways. And the idea for this session in particular is to showcase the work of PhD students, many of which who are working under the SHEAR program and funded by them. And so they're going to be presenting their work, their ideas, their insights, and the goal and the hope is to create some sort of virtual space in which you can all exchange with them, with each other, over the course of these next 55 minutes. And so, so the session is going to be run as a series of panels. Everybody's going to have about 5 to 8 minutes to present. And we're going to be taking questions at the end of each session. But one of the things we were hoping to do is kind of create a virtual copy space in the chat in which you can ask your questions, and we would encourage you as much as possible, if you're comfortable, putting your email addresses along with your questions, because we know that time is limited, and so we're going to be allowing the students to answer you directly if they don't get a chance to answer your question quickly personally this way. They'll be able to write to you and connect, and essentially the equivalent of giving out your business card at the water cooler. So we wanted to present that opportunity as well to everyone. So without further ado, and because our time is limited, I'm going to share my screen and introduce you to the first speaker. Can you all see my screen? Yeah, fantastic. All right, so, and I would encourage as well everybody who's here to turn on your cameras and kind of, make it as personal as possible in these difficult circumstances. So, all right, so I'm going to stop talking, and I'm going to hand over the mic to Niraj Shah, who's a doctoral researcher at Imperial College London, and he's going to be talking to us about his work using low-cost sensors for flood monitoring. Niraj, over to you.
Okay, thank you, Dorothy. Hello, everyone. I hope everyone can hear me. If not, then please contact Dorothy. Okay, she already said that I'm a PhD student at Imperial College London. Today, I'm going to share our work on development and application of low-cost sensor network for flood monitoring and forecasting. Okay. So first of all, let's take a look at a typical flood forecasting model. So when we see a typical flood forecasting model, what we see is an input block, which basically consists of the forecasts of rainfall. And then there is a model block, which work on the input and provides us flood levels. Now, we all know that the flood forecasters are not perfect. There are different sources of uncertainties associated with it. One of the source of uncertainty that we often come across is lack of data, and when available, maybe lack of quality data. And we all know that the model that is used in flood forecasting system are good as the data used to calibrate them. When I'm saying data, I am basically talking about river level or stage and river discharge data. So that is why we built the sensor, uh, because we mainly wanted to increase the concentration of data in certain areas and use the sensor in hydrology. Okay, so let's take a look at the LiDAR sensor that we have built. On the right hand side, you can see our latest prototype of LiDAR sensor. So as the name suggests, LiDAR basically works on the principle of light waves. Now the novelty of our sensor lies basically in selection of its wavelength, which is near infrared, because at this wavelength, the light waves get reflected from the water surface, so that we can measure the distance between the water surface and the LiDAR sensor. The other two things that I want to highlight here is the range of our sensor, which is pretty good, like 2 to 40 meters. And other thing is its property to incline. So you can position your sensor on the bank and you can incline the sensor up to 40 degrees, which is very good if you want to place your sensor in mountainous region where rivers are quite below the banks. Uh, Another much important thing is cost. Obviously, we should not forget about the cost. So cost of our sensor is much cheaper than the industrial grades. Okay, can we move to next slide, please? Thank you. So after we built the sensor, we tested our sensor in lab and field conditions. I want to just show you one or two key results here. So one of the key result here is that when we place our sensor over water surface, and when there is more roughness on water surface, what I mean by roughness is like the more turbulent water is, or when the velocity of water is more, the the data that we gather from sensor is good. Basically, the standard deviation between the data is very less, as you can see in figure C, because in this case we placed our sensor on river Thames. Also, there is little to no effect of turbidity of water on sensor data, which is good to basically record flood data, because we often don't have flood data. And as sensor are non-contact source of measuring river level, they are good to measure the flood data. So it's good in monitoring flood. You can read more about our sensor and the sensor testing in the open access article published in WRR, which is shown here. It's also in the reference section. Okay, so after we saw the potentiality of our sensor in measuring high resolution river stays, the next step for us was to find a methodology to estimate river discharge. Now we all know that most of the times people use rating curves to measure discharge, because that is how it's been done, and it's cheaper. But we know that rating curves are fraught with uncertainties, mainly because like they are based on a steady flow assumption, which says that the depth of flow in a river does not change with time. Now we know that this is not practical, so we need to have unsteady flow estimated. So for that, there are various methods in the literature. So one or two method is that they use water level data or stage data from two locations, and then they solve the governing equation shown in the slide to estimate the discharge. Now the problem with those methods are that they solve the governing equation in conservative form. By that, what I mean is by omitting some terms from the momentum equation. And those methods are valid for prismatic channel only and where there are no lateral flow. So it seems a bit impractical to use them in real life condition. So what we propose is, instead of using water level data from 2 or 3 locations to measure the discharge dynamically continuously, we propose to have an array of sensor on a river reach and use the stage data from array of sensor to estimate the discharge. So the tricky thing is, how do we solve the governing equation in its full form? So we can develop our own sensor, but so that limits the sharing capabilities. So what we did is, instead of developing our own sensor on a solver, we use widely used HECRAS, a river modeling software, to solve the governing equation in its full form, and we tap on our computational efficiencies by running the HECRAS in batch mode by using it with Python. So that is how we do it. Okay, can we move to next? Yeah. Okay. Okay, sorry, I forgot to mention one thing. So when we couple HECRAS with Python, maybe there are two things like that is worth mentioning here. The first one is that when we couple HECRAS with Python, we can use all the functionality of HECRAS. And the second thing is, the both HECRAS and Python is open source, so we can share it with large audience. Okay, so here I'm going to just show you a model simulation of our methodology. So we estimated river discharge dynamically by using stage data from 2 locations, the node 1 and 5, which you see here. And then again, we estimated the river discharge that with stage data from 5 locations, 1, 2, 3, 4, 5. You see the rating curves on the left hand side is the one estimated with stage data from 2 locations, and on the right hand side is the one estimated with 5 locations. So instead of showing only one rating curve, I show you 5 rating curves, which were the like top best 5 rating curves. Now you see there is only slight improvement when we increase the number of stage data on the right hand side. Maybe you'll have more time to look at it afterwards and see. So there is some improvement in discharge estimation by increasing the number of stage data. Okay, one thing that I want to highlight here is, just a second. Yeah, one thing that I want to highlight here is, so by using the methodology, we can not only estimate one rating curve, but we can estimate ensemble of rating curve and use the ensemble rating curve to calculate different uncertainties associated with different discharge types. Yeah, thank you. If you have any question, please feel free to write them in the chat. Yeah, thank you.
Thank you so much, Niraj. Yeah, I think we're going to, actually I have a question. What's next in your research?
What's next in my
research? What's the next step?
Okay, so now we have developed a method to estimate discharge by using array of sensors. Now the next thing is to find the optimal network combination. So how many sensors you need to measure the river discharge dynamically in real time? What should be the spacing between those sensors? That is the one thing. And the next thing is, if you can use the network of sensor to estimate, like to forecast flood in real time.
Brilliant.
Yeah.
Well, we'll keep an eye out then. Thank you so much. We're going to keep an eye out on the chat, and we'll send you people's business cards as they go. All right, let's go to the next presenters, who are Shriyasi Chowdhury and Peter McGarren, who are going to be talking to us about using mobile phones in DRM. Both of you, I'm going to let you turn on your mics and take them.
Oops. Dorothy, there were actually questions.
Oh, were they really? Excellent.
Yeah. Louisa Whitlock is asking, what size of river were you testing the discharge estimation approach on?
Okay, so for now, we did some model simulation where we have different flow conditions and different types of rivers. For example, the one that I showed you was 50-meter wide, and the depth is, we assume. Then there are other rivers with 400-meter width that we test, and currently we are collecting data to test our method in field condition with different types of river, all kinds of sizes.
Awesome. Neeraj, we'll get to the other questions yeah, at the end, I think. All right. All right, so backing up. Yes, take it away, you two.
Thanks. Hi everyone, Strassi and I will be presenting about the role of mobile phones in our respective PhD research projects. We're both based at King's College London and part of the SHEAR studentship cohort. Next slide. Sorry. Is anyone else's slides not moving? Sorry. No. We'll discuss how, sorry, back again. We'll discuss how we use mobile phones in our projects and the opportunities and challenges this created. We'll then provide some recommendations on using phones in disaster risk research, as well as some avenues for future research on this broad topic.
So my name is Shreyasi, and I'm a third-year PhD student at KCL. I'm working on developing a Bayesian belief network using expert elicitation on hazard interactions, specifically those that include landslides. Expert elicitation is a process that obtains judgments from relevant experts and then combines them robustly. And Bayesian belief network is a direct acyclic graph with a set of variables and a direction of causality between those variables. Now, this network produces a probability estimation of any probable or possible event. So in my research, to get this probability estimation, I will be interviewing experts. And I am using or accessing this network on Darjeeling district in India.
My research uses assemblage theory to understand the complex interrelationships that lead to the emergence of multi-hazard disaster risk in Kalimpong district. This borders Darjeeling district, where Shreyasi and Lanslip are also doing their research, but our projects are quite separate and have very different approaches. I spent a total of 6 months in the field doing qualitative research, including focus groups, interviews, and ethnography. Most of my interviews were with people affected by landslides at the so-called grassroots level, but I also interviewed key informants such as officials, academics, and NGO workers. My mobile phone was integral to most parts of my field work, from contacting participants, organizing field visits, and recording interviews. I also used my phone's camera for field photography, and the geotag function on Google Photos allowed me to map the photos and just the landslides I visited when I returned to the field. I'll return to that later.
So just like Peter, I used mobile phones to approach, to interview, and to record the participants, and also to ask several international experts to rate landslide triggers and causes on a questionnaire that was developed on Google Forms. So mobile phone was pretty much integral even in my research. Also because most of my interviews were done from April to September 2020, which was during the lockdown period. So everything had to be converted online. Now I had to call experts on normal calling or like WhatsApp calls or through WhatsApp messages in India, because most of the people preferred that. Also, I used mobile applications like audio recorder or WhatsApp for my interview process. So that is one part of the research. The other part of the research where I will be using mobile phones is to develop a mobile-based serious game to communicate about the hazard interactions to the local people. Now, I will be discussing more about this in the later slides. But for my research, since the experts included academicians, technical professionals, local people, or indigenous people, it helped me increase the scope of my research, which is one of the first opportunities that I will be discussing in the next slide. Can you go to the next slide, please? So in the major parts of India, people prefer being contacted via normal calling or via WhatsApp message rather than via emails. And one of the other points is that the local people do not have access to computers or high-end mobile phones where, you know, Skype or Teams would work, or even a very good Wi-Fi. So using mobile phones helped me involve local people or indigenous people in my research. Obviously, that brought in the limitation of not being able to study or understand their body language, but I had to deal with that. Also, I did face some issues of recording the interviews because of poor mobile or wireless network. I also did use mobile phones to rate rate landslide variables on Google Forms, as I said in the previous slide, but some of the local people did not want to or could not access Google Forms. So that was another limitation of using mobile phone. On a very different context though, another challenge that I faced was the ethics form that I had to update. I had not realized that I would be accessing personal mobile numbers of academicians or technical professionals until I went out to the field. So we need to look into ethical issues as well when it comes to using mobile phones in the research. Next slide, please.
On opportunities and challenges, I'll be talking more about technical points. So my first point relates to accessing mobile data in place of Wi-Fi. The Indian government has invested a lot into mobile internet coverage recently, meaning that access is now widespread and reasonably strong in even remote areas. So not relying on Wi-Fi in the field is useful for all the methods I mentioned previously. However, being an international researcher did make it a little bit difficult to access those SIM cards, but this was easy enough to overcome with some help from Indian colleagues. And then remaining on technical issues, obviously modern mobile technology allows you and enables you to do a lot of your technology related field work on one device, which is really handy when visiting remote areas. However, there are also like the usual challenges of reliability, technical hitches and battery life. So the main point here is that you should always have a backup plan for your mobile phone. Next slide. In the previous slides, I mentioned that I used the geotag function on Google Photos to track the landslides that I visited. I then realized from this information I was able to create this kind of map on Google Earth showing the landslides that I visited when I was in the field, which this area shows Kalimpong district. And then from this, I was able to like scroll in and zoom and then get a different perspective of the landscape that I had visited. And this is really useful if I'd forgotten to take a GPS reading or something, because it just saved it automatically using my location, which was really handy. Next slide.
So to bring an end to our presentation, we will both leave you with certain recommendations. So the first recommendation is regarding the research design implications of using mobile phones in your research. So from the interviews that I took, one of the major things that I figured out is that there's a clear division in India on the urban people and between the urban people and the rural people on using mobile phones, as I had already discussed in the previous slides. But it is also very clear, this distinction is very clear when we talk about computer games versus the role play games or the board games. One of the distinction that we can see is in the graph that is shown here. Now, even in Darjeeling during the interviews, it was clear the local people wanted to have more of more of role play games or board games rather than mobile games. So I think I would recommend here that please understand the role of mobile phones that is different in different geographical contexts or even in cultural and institutional contexts, and define your research accordingly. I faced an issue with this when I had not even thought of, using the mobile phone in such a huge aspect in my research. And this will also help you in including indigenous people or local people into your research, because they generally do not have access to such good mobile phones that we generally have. And I would also recommend that please understand how mobile phones might make your research design different and make it more inclusive from the outset of your project rather than in the middle of the project itself. Next slide, please.
So this recommendation is less about the role of mobile phones in our research practice, rather it is about some findings from my research relating to the role of mobile phones in disaster management practice in Kalimpong, which might be seen elsewhere too. So as can be seen from the quotes, mobile phones are changing the relationships between officials and citizens in the context of disaster management in Kalimpong. These changes can generally be read as positive, but there are downsides, particularly for officials with large portfolios who feel overworked or always on duty. But I'll move on just because I know we're nearly done. So yeah, I'll just leave you with some more practical recommendations for using mobile phones in doctoral disaster research. Thanks.
That was brilliant. Thank you, both of you. That was super interesting. I think there are questions in the chat, Stefania, if there are any. I think I can see them coming in.
There is a question from Louisa Whitlock that asks, were there any particular groups that you found difficult to reach, even by mobile phone? Are there groups which don't own or don't have access to them?
Yes, there are. In Darjeeling itself, there are some of these people who live in the deep forests. And well, Darjeeling actually has been turning into an urban jungle right now. But still, there are some of those people who do not have access to the mobile phones. A very great example is my own grandmother, who is from Darjeeling, and she still does not own a mobile phone at all.
Yeah, I'd say there are some, but surprisingly, like fewer and fewer, like even people that you might not think, like that is extremely widespread now in India. And like with mine as well, it was more of a snowballing thing. So if you found someone on a mobile phone, they would often just introduce you and pass you on to other people. And if they didn't have a mobile phone, they'd just take you to them. So snowballing approach was really useful in that aspect.
What a great opportunity. I'm sure people are going to have a bunch of more questions. So everyone would highly recommend you put them in there with your email addresses, and both Peter and Shreyasi can get back to you via email. So thank you both so much. We're going to jump to the next presenter, who's Gaurav Adwadi, who's a PhD candidate as well at King's College London. Gaurav, I'm going to suggest that you turn on your mic if you can, and I'm going to give the mic over to you.
Yeah, thank you. Thank you,
Yeah,
Dorothy. My PhD title is actually Understanding the Transboundary Impact of Multi-Hazard Early Warning System and its Cultural Context, like how cultural context affects in disaster risk management. And this specific topic that I'm trying to present now is based on the complexities in risk communication for flood early warning system. We basically focus only on the technological side, but we tend to omit the social side. So what are the needs in the ground, like that is what I'm talking about in this presentation. So next, please. In the background, the early warning system is recognized as a crucial mechanism for disaster risk reduction. And the UNISDR specifically from Sendai Framework of Action mentioned it, and 2015 marks as a time where there's a shift from managing disaster to managing risk. And in this context, like there has been a lot of technological advancement going on, but despite the technological advances, the biggest shortcomings still is the technology, or the early warning system is not like reaching the people, or it is still failing the people at risk, mostly in developing countries like Nepal and India, and particularly the very deprived ones. And the effective early warning systems not only require sound technological basis, but also depends upon how risk communication or risk information is understood as well as interpreted in a particular society. So with that background, I want to move next. So my study area is in Kosi River Basin, which is a transboundary river basin between, my study area is between Nepal and India, but the river basin is quite big. And the study is based on 90 interviews taken at different level with local community, as well as scientists, experts, as well as with the government officials and experts from both the countries. Next, please. Talking about the complexities, Kosi River is a transboundary river that originates from China, that flows from Nepal and reaches India. And annually, the Kosi causes widespread flooding and inundation in Nepal and India. It's like an annual phenomenon in Bihar and in Nepal. So every year, flood-affected people take refuge in embankments. They have to live in the embankments for about a month. And these living conditions are extremely like, they don't even have any toilet facilities or electricity or cooking fuel. They have to rely on, like, live on the mounds under the makeshift huts. can you turn the next, please? There's a picture. And you can see that people living in the makeshift huts, and the condition is like that, like you have to fetch fuel, wood for fuel and those kind of things. And women suffer the most because they have additional workload during those times, as well as women suffer harassment while they have to go to toilets, or like there are lots of gender-based violence are recorded. And to avoid that, like there has been a lot of technological advancement in Nepal and Indian side. Department of Hydrology and Meteorology is now sending targeted mass SMS to all the people in the floodplains in Nepal. And similarly in the Indian side, Bihar State Disaster Management Authority is also sending messages, but only to the key authorities that are in the response institutions, not to the all people. And also, the flood bulletins are issued in the website in monsoon season twice daily. And there is also web-based real-time information displayed, and social media platform like Twitter and Facebook are also used. Like in the picture, you can see the text message being sent. Next, please. But the major challenge is when I talk to the people in the ground, what they said is people don't get those text messages because the most poor ones, they don't have smartphones. And people say that like even for limited people, like there's only one mobile phone in a household, and the male leader of that household carries the mobile phone, and he's usually like based in daily ways kind of work, and he's away during the day, and like they don't actually get the information. All the people like family members don't have that information. And in Indian side, only like limited people has the access to those information, like the flood is coming, or like go to the safe place. And only the people who are around the key leaders, or like Thanedar or the police officer, they get access to those information, not all the people. Like most of the people mentioned in India, they like they only know about flood when they see the flood. Like when they see the water, they know that the flood water is coming. And also the information what is being disseminated, it says like the flood level is reaching, has reached 2 meters, and the people who are at the river bank, they go to the safe place, and it does not translate like whether it will affect me or not, or those kind of things. And also the risk information is initially it used to be sent in English language, but now they are sending it to Nepali, and in the Indian side they are sending Hindi. But the people who are living there in the floodplain, they speak Maithili as their first language. Most of the people only speak Maithili. They don't understand, like they understand bit, but not, they are very fluent in Hindi or Nepali. So those are the complications. And next, please. And the major complication is like the institution side, they are scared to issue the false alarm. They don't want to lose the institutional credibility. So what happens is, due to with the model forecast, they can predict floods 3 days in advance. But what they do is like they only issue or the push text messages about flooding about 1 to 2 hours in advance, because they don't want to like take chances by issuing false information. And what if there's no flood and they issued those text messages? So that is their perspective. And what people said is for the limited people who receive those messages, they say like, yes, we receive messages, but like 1 to 1.5 hours before flood is like when we are already surrounded with water, we don't need any information like the flood is coming. We already know that. So it is very much inadequate response time to save our life, assets and commodities. And those were the complications. And also what people said is like during the monsoon season, there is no electricity, there is no internet access, like with the cloud, there is like a network outage, and those also like disrupt or hinder the process of risk communication through those mobile devices. And also like most of the information is like a given, like scientists create information and they give to the people, like this is the way how you act. Like when we push the message, you just run away and go to the embankment. There's no such thing as like a co-production of knowledge or collaboration with the communities. That's what I found when I was in the field. Next, please. So the key learning from this study is like, first of all, we have to understand that risk communication is a social process of meaning creation. We create meaning with the community, what risk means to them in terms of their lives, in terms of their livelihood. And we, with people and the scientists collaboratively, they devise a solution. And in that way, that is a proper risk communication. And it has to be in that way. And first of all, understanding how community interprets the risk information and takes it into action is very vital for early warning system. And that social side has to be like given emphasis, just like the technological side. And risk communication in Nepal and India employs basically one-way communication, where government institutions give information to the affected people, but not information, they're not co-producing the information at all. And early warning systems use are neither inclusive nor flexible enough to incorporate local knowledge as well as decision-making process. These are the key learnings and findings from my field work. Next, please. And the final, the recommendation from this study is like the early warning system should be people-centered, not technological-centered. And it has to be impact-based forecasting. And there's no such thing as community-based, like there's no such thing as community who work coherently, or like there's a group, generic group who works in a certain way. But community means different sort of people with different vulnerability and different needs and different capacity. And we have to cater in that regard as well. And also, like my recommendation is local people's participation should not limit just to their target groups. The participation is required for knowledge co-production, and mobile technology should also be used for capacity building as well, because understanding risk is the main thing in all those disaster risk management process. Thank you. So these are my contact details. Thank you so much for attention.
Thank you so much. What an interesting and important topic, and one I'm sure that we'll find a lot of resonance for a lot of work that we do as humanitarians as well. So thank you so much for sharing. Stefania, are there any questions in the chat to go through quickly?
Not yet in the chat, but I have a question. I would like to know if, based on your experience, you have any advice on how to conduct a co-production of risk communication with the community?
Yeah, the first step is like, you don't just make the project by yourself and go to the ground level and like try to adapt your project based on how can people be needed. Like the co-production can only occur when it is like a demand driven. You have to first of all devise the project, know what is the need with the community, and understanding the need at the community level must be the entry level for co-production of knowledge. Like you devise your project all set up in your office, and then you go to the community, and in that way it would be very hard for people to digest those like project need, and also like for your project to adapt those people in your already built up system. So the entry point should be from bottom up and from demand driven pathway, not like a supply driven. That is what I think.
Fantastic. And what a lesson for people making and using technology, I think. Thank you so much. We'll go to the next presenter, who is Sajad Hussain, who's a PhD student in environmental science at the University of Reading. So I'm going to put myself on mute, and I'm going to give you the mic.
Thank you, everybody, and welcome to my presentation. So I am a PhD student at the University of Reading. So I am working on extended range hydrometeorological forecast for the improved flood early warning for Bangladesh. So in my work, I am just focusing now how GLOFASS forecast can predict flood timing and duration. And we have a case study for 2020 floods in Bangladesh. So my study area is in the Brahmaputra basin. It is basically a transboundary basin, and that consists Bangladesh, India, Bhutan, and China. So, and it has a diverse landscape. I mean, high mountain area as well as floodplain. It's a bit complex landscape. And the basin is located in high monsoon rainfall regime, particularly Assam, Sub-Himalaya, West Bengal, Sikkim and Bhutan that got the during the monsoon huge rain, and from geographical as well as climate condition, flood here is an annual phenomena during the monsoon between June to September. So if we look at the annual variation, so we can see here the strong interannual variation in the flood timing, duration, and magnitude. And here the blue color shows the lowest flood level, and the red is the highest flood level. And 1998 we had the longest duration floods that was more than 2 months, and this year monsoon we have flood 43 days. It is the second highest duration floods. And as I have mentioned in the Gantt chart, there may be multiple flood pulses in a monsoon. So this year we got the 3 monsoon flood. So then it is clear from my last presentation why we are looking for the extended range forecast. So we need to predict the flood timing and duration during a monsoon, and short range forecast that flood forecasting center in Bangladesh are practicing. They cannot give forecast after a few days. So it is very short time, and particularly for agriculture, it is very important for the farmers to know when flood is coming in a monsoon month and how long it will continue. And presently, flood forecasting earning center providing forecast up to 5 days in short range. And in FFWC, they don't have long range forecast like 30 days. So under the research, during 2020 monsoon, we have just looking how GLOFAS forecast performed in a particular flooding event to predicting the time and duration. So first, here I am just presenting a flood hydrograph for short range forecast that flood forecasting center used during the monsoon. So the left side hydrograph, you can see flood warning was issued on 2020 June, and the black line shows the observed water level. So it was clear that they were not able to predict the flood. Even 3 or 4 days before, actual the onset. And if you look at the second right side hydrograph on the several days from June 7 to 12, so we can see here that they can just predict the onset flood only 2 or 3 days, and they can give a trend. And even in sometimes, for instance, July 7, their forecast was downward. That means it shows 5 days before that flood water may not rise. And so what we have learned from this short range forecast, that it cannot give you a detailed information beyond a certain time limit. So now, if we look at the GLOFAS forecast that we are piloting under my research, so this is the hydrograph for the first flood event between June 26 to 7. And we can see forecast from June on to 5. There was a little bit early peak, but when forecast issued on 15 to 16 June, it was clearly shows the onset on 26 June and the flood duration almost around 10 days. And actual observed flood shows the onset 26 June and the peak is 30 June. So almost similar to the observed. And for the second flood event, we can see the more consistent flooding compared to the first. GLOFAS forecasting was more consistent compared to the first event. And if we look at the onset, it was 12 July and peak was 17 July. And observed was 12 July and 16 July. And the vertical green line shows the probable flood duration. So from the observed data, it was almost, for the second flooding event, it was very correct and consistent, the observed flood and the GLOFAS forecast flood. So here I have just presented GLOFAS forecast and EF5 reanalysis data, because we don't have observed water flow data right now. So it clearly shows the 10 days forecast, flood duration, and the onset date. And interestingly, the important thing was after August 7, there was no significant flood event. So this message was very important for the farmers. Okay, so under this project, we have communicated the forecast information to the major stakeholder like government agency, humanitarian agency, and there was a FBF activities by UN agencies, and they have initiated their activities 10 days before the actual flood event. And we have given information like how much ensemble for number is going to exceed the flood threshold. And for instance, when we communicate with the farmers, so after 9th August, they are starting to planting their seeds and preparing the lands. And you can see it has a huge impact for the farmers to take the decision. So these are the figures that global media has got the attention, how fast FFWC and University of Reading was able to forecast the flooding event. So in conclusion, what we are trying to say that GLOFASS has the potential to predict the monsoon flood timing and duration with a sufficient lead time, and it is very important for the farmers when there will be no further flooding event. And also when we communicated in our pilot project, farmers was very happy, and we are going for the large scale dissemination maybe in the coming monsoon. But there are also something that there might be some early peak or delay peak with the increasing lead time. This is a bit obvious. And also monsoon rainfall, as it is a very vast basin, so there is a special distribution of monsoon rainfall, so that may have impact on the controlling the flood peak. And we have found some overestimation compared to the GLOFASS reanalysis flow data. So this is, we will look in future. So in the next phase, we will assess the GLOFASS statistical skill of GLOFASS forecast. Yeah, thank you everybody for having patience.
Thank you so much. It's brilliant. I know it's a story that we've been following closely and super interesting. I think there's a lot of questions as well in the chat, but I can't see them. Stefania, is there any quick one maybe? And then we can give the rest to Suzad by email.
Yeah, so I don't have specific questions in the chat on this presentation. I do have a question because the GLOFASS overestimation. Do you see questions on this presentation? Have I missed something? No, right? So we go with my question. The GLOFASS overestimation is something that I hear from a lot of places. So do you have an advice about what could cause the overestimation of the peak and how to handle it?
Yeah, so this is very good question, because GLOFASS giving the forecast based on threshold. So first at this stage we are looking the threshold, that how it is crossing that particular flood danger level or flood severe level. But to compare with the bias, like how it is our forecasting, so there is also limitation on uncertainty in observed data. So that is we will explore in the next phase of my research, as the observed data in the developing country, particularly river flow data, has got some problem, as Neeraj was mentioning earlier. So you can imagine, yeah.
Awesome.
And Azad, look at the discussion in the chat, because Paolo has also some ideas. So maybe you can yes, continue the discussion.
Yeah, thank you.
Yeah, that sounds great. All right, so going on to our last presenter, last but not least. There we go. Eileen is a PhD candidate in Amsterdam at the Vrije Universiteit in Amsterdam at the Department of Environmental Studies. Eileen, I'm going to drop this over to you. I'm looking forward to
thank you. So my name is Eileen. Hello, everyone. And today I'm presenting a work I've been done during my master thesis at the TU Delft, which was in collaboration with 510 as part of the SHEAR iPace Malawi project. The research was on drought forecast information for smallholder farmers in Malawi. Next, please. Smallholder farmers in Malawi rely on agriculture to sustain their family for food and income. And drought can lead to food insecurity, which can affect the families dramatically. Therefore, organizations are providing drought forecast information to increase the preparedness of farmers to drought. However, that information is not always tailored to the farmers itself and results in limited uptake of that information into the agricultural decisions. So in our research, we started actually by looking, started by looking at the situation of the farmers itself, like what information do they currently receive, what information do they need, and what can be improved. So I will first sketch a situation of the farmers. In Malawi, there's a dry and a rainy season. And in the rainy season, the crops are grown. And we found that there are a few very important decisions that can be made in the dry season, which influence on whether a drought, a drought in the rainy season is expected or not. So for example, in September, the farmers decide what type of ridge to make. When a normal rainy season is expected, they make normal ridges. However, when a drought is expected, they may opt for making box ridges that better retain soil moisture. So information on whether there'll be a drought or not may inform what type of ridge to make. This figure also shows the onset of the rainy season can inform decisions like what and when to plant seeds. So throughout the rest of this research, this is the information we would like to predict at these moments in time. Next, please. Currently, farmers already receive information either via local knowledge or via the National Meteorological Office. The forecast received through local knowledge is based on meteorological indicators, which include wind and temperature observations and feelings. For example, if there are strong winds or cold temperatures in certain months in the dry season, they expect a drought in the rainy season. Farmers also receive information from the National Meteorological Office, and Alexia Cavell has done more extensive research on this part. And she found that thanks to the implementation and local services, such as extension and radio services and downscale forecasts, drought warnings were trusted more and used by the farmers. It was also found that the guidance and advice that comes along with that forecast is very important. However, the decision on when to act is based on local knowledge. So we would like to incorporate next one, please, those local knowledge indicators in a scientific forecasting approach. Firstly, we want to explore, can a forecast model include local knowledge indicator to predict drought? And so here wind, temperature, but also ENSO observations in the dry season. Can it predict the drought information in the rainy season? And we see drought information as the timing of the onset and drought expressed in the number of dry spells and a certain composite drought index. And secondly, can we predict it on time to be relevant for the decisions of the farmers? Next one, please. Maybe I will skip it a bit because of the time limitations, but this is the model, the setup of the model, and it incorporates data and sets certain thresholds that are optimized. Next one, please. These are the results shown for the prediction of the number of dry spells at different stations, so the dots, at different thresholds, which are the different colors. And the gray area represents the area where the forecast has no skill. The further the dots are away from that area, the better. So from the figure, we found that local knowledge indicator have a predictive value, but it's hard to predict, for example, 5 dry spells or more. In this example, we've not looked at the lead time of the forecast yet, but what if we want to predict the relevant information on time? So the second aim, that's the next one. These are the results shown spatially, and in short, the greener the better. And the white dots represent the stations together with a triangle, which represents the onset, and the circle, which represents the results for dry spells. And on the left, we see the hit rate, on the right, we see the false alarm rate. And we see that the results differ per climate region, and that the climate region 2 has better results. Well, this can have various reasons, maybe because of the lake, so the blue lake, that can influence certain wind processes. Maybe finally, some last remarks. It's important to tailor the forecast information to farmers. And we also have 2 papers coming up. One is recently published by first author Carousel, and I'm already also writing a paper. If there are any questions for this last half minute, I'm happy to answer them. And thank you for your, thank you.
Hi, Eileen. Thank you so much. There are questions in the chat, and I know I'm going to get in touch with you if you don't mind for some of the stuff that we're doing. It'd be brilliant to be in touch. Stefania, if there's a quick question, we have a minute left, but just in case, but just in case we do get cut off, everyone, wanted to thank you so much for joining. It's kind of an opportunity for everybody to be in touch and kind of exchange on all these ideas. So yes, please put your emails in the chat if you want to get in touch with any of these presenters, and keep an eye out on their research. They all have papers coming out, and their work is continuing, and so we'll all be looking at this with extreme interest. So thank you all so much. Oh, Eileen, there are questions in the chat coming up. Stefania, do you want to go ahead?
Yes, there is. I just for you one question that is how localized are the forecasts from the local knowledge indicators? To what extent are they useful across a wider area? It's Louisa Whitlock.
Yeah, so we did research in 3 different districts, and they all had similar similar indicators, and we only looked at the wind and temperature related indicators, but yeah, they were very similar. So the knowledge was quite widely spread, let's say, mostly in rural communities. Yeah.
Fantastic. Keep an eye out for more questions coming your way, Eileen, I think. And on that note, everyone, thank you so much for joining us. Thank you for coming to Understanding Risk. Hope to see you at many other sessions, either this conference or over the year, and hopefully all in person in 2021. So take care, stay safe, and yeah, thank you so much for joining us.